Okay, this is the review for the final. The final is a bit shorter than the others. The other exams are nominally 90 minutes. This one will also be 90 minutes, but you have a maximum of an hour and 50 minutes to do it because we'll have to leave for the next class. The score is 3 questions, each 110 points. 100% score is 300 out of 330. They're adjusted in the same way. And there are 3 questions. One on pipe networks, which is chapter 10 and 11, or section 10 and 11, mainly 11. One is on external flows, looking at the velocity of bodies in motion and the forces applied on them, which is 12 external flows, and open channel flows, which are 13, which is a gradually varying flow using specific energy. So those are the question areas. So if you want to look at the equations that you would need to give you an idea of what the questions might be, then maybe we'll just go through that briefly. Let's see. In terms of dimensionless parameters, you've already derived these in terms of Buckingham pi, but the dimensionless parameters that you might want to be aware of: a Reynolds number, the ratio of inertial forces, velocity, density, and length divided by viscosity, inertial forces to viscous losses, and Euler number, which is a force or a pressure divided by density times velocity squared. So pressure forces divided by inertial forces, which is actually the same as the magnitude of, if this is a force, rather this is a pressure. If this is a force divided by an area, which is a pressure, over rho v squared, then this is equal to a force divided by a pressure divided by a velocity squared and an area. And if you remember this equation here, if you put a half before it, is exactly the same as the coefficient of drag or coefficient of lift, depending on which direction that force is applied. So Reynolds number and Euler number are important components, and of course the Euler number is really, except for a magnitude of a factor of 2, equal to the coefficient of drag. The equations that you'd want to be able to deal with pipe flow networks are the energy equation. Remember that it's a pressure force, elevation, or force per unit volume, I guess it is, and the inertial term, plus a pump head, is equal to a pressure force downstream, or the pressure head rather, the elevation head downstream, the velocity head downstream, and plus the losses, which are summed. And the losses fall in 2 categories, I guess, right? The ones which are minor, which are given by a friction loss v squared over 2g, and the major losses are small incrementally, but as they sum, are a friction factor, a length, a diameter, and a velocity squared over 2g term. I guess important to note again, if you're doing this between upstream and downstream, that the downstream is on the right hand side and the upstream is on the left hand side. Velocities are always positive. You certainly know this. If you have a pump here within this, then this term is positive for a pump and negative for a turbine. Elevation heads are measured vertically upwards. pressures are positive. This is unit weight. And the pump head is equivalent to the power of the pump, which is in watts, divided by gravity times density times the volumetric flow rate. The volumetric flow rate is just equal to the velocity times the cross-sectional area. And so we know this term, these are always positive. Minor losses and major losses are always positive. And this is always downstream, and this is always upstream on the right-hand side. There's a certain commonality, I guess, between the problems that we've dealt with. And certainly we've talked about Moody charts in great detail, where this is indexed as the flow regime relative to the Reynolds number, which is, I guess, we've used diameter of the pipe, I guess, as the characteristic length by viscosity. We've defined some different regimes. For pipe flow, this is something like 2000 for this transition from laminar to turbulent. This is the magnitude of the friction factor, but it's also the magnitude of the coefficient of drag, essentially. And it's also equivalent to, in some respects, the Manning coefficient. So this is the friction factor for open channel flows. Coefficient of drag is for external flows, and the Manning coefficient is for open channel flows. And the important difference, I guess, between these regimes is that the friction factor is constant. These are values for relative roughness. So this is equal to roughness. Relative roughness is epsilon roughness over diameter. And these are laminar behaviors where this is some coefficient divided by Reynolds number, constant divided by Reynolds number. And the magnitudes of the friction factors or drag coefficients or Manning's formula coefficients are constant in this regime where they're turbulent. Almost all the flows in open channel flows are turbulent, and so you can use a constant magnitude of this. They aren't necessarily that way for these, for flow in pipes and for flow around objects. And so that's worth remembering. The indexing of this, if it's a non-circular pipe, is through the hydraulic diameter, which is equal to 4 times the cross-sectional area divided by the perimeter, which is just, if it's a duct, then clearly the area is this, and the perimeter is just the length around the whole component. So that's the energy equation, which is used for pipe flows, single pipe flows as we've used it. If we look at pipe networks, then they come in really 3 varieties. Those which are in parallel, those which are in series, and you've seen these figures before, I think, between upstream and downstream, and also those which are maybe branching. And so they differ slightly in that here the flow is equal to the sum of the volumetric flow rates, but the head loss between upstream is constant for all pipes. In this, the flow is constant and the head loss is summed as you go down through here from one to the other. And in the final case, the head loss in pipe, if this was pipe 1, 2, and 3, then the head loss in 2, because they have the same pressure here and the same pressure typically at the outlet, is equal to the head loss at pipe 3. And so in this particular case, you can write Bernoulli for one circuit, Bernoulli for the second circuit. You'll end up with 3 flow rates, and you have to close it by the fact that Q1 is equal to the other two added together. So these are the flow rates in each of the individual pipes. So these are basically the requirements for each of the individual networks. The head losses are constant across this because they have to go from this pressure to this pressure, or this head to this head. In this case, the flow rates are constant across here, and the head losses are cumulative. And in this case, you have to write Bernoulli twice, once for the upper network, once for the lower network, and then tie the velocities through with continuity, and to solve for 3 flow velocities as a function of 3 equations, typically. So that is week 11, I guess. This was 10 that contributed to week 11. And for external flows, typically external flows, there is a force that's applied on a component. It has its weight, and there's also a drag force which acts in the opposite direction to the motion in any case. And so we can identify this as equal to the weight plus the drag is equal to, in this case, the buoyant force or any kind of force acting on it. And so we can certainly rearrange that in terms of the drag being equal to the buoyant force minus the weight. And we can define the drag in terms of a coefficient of drag, where this is the coefficient of drag, which is equal to a drag force divided by a half, just by convention, rho v squared times a, which is the same as equal to, if you split it out as a half rho v squared d over a, this is basically a pressure. And so, as we said earlier, this is really a coefficient of drag is an Euler number, as all of these terms are. And so the graphs look somewhat similar to this, also in terms of Reynolds number and the scaling with Reynolds number for the flow regime. And so typically what we end up doing is trying to solve in 2 particular ways. And the 2 particular ways are either for the laminar case or the turbulent case. So turbulent is easiest because you can just rearrange this in terms of a coefficient of drag, and you can resubstitute this term here into here, and you're left with an expression where the only component to solve is for the velocity. So I guess you can always rewrite this as equal to the drag is equal to coefficient of drag multiplied by a half rho v squared a. And if you know what this is, or substitute into here, and you know what these other 2 components are, you can solve for the one unknown. And for laminar flow, you can do exactly the same, except now the coefficient of drag is equal to typically a constant divided by Reynolds number. And so if you make the substitution into here, and this substitution into here, then you end up with a coefficient drag, a velocity squared term, but a term that includes the velocity here. And so the solution for laminar flow ends up being as a function of velocity, and for turbulent flow it means it's a function of velocity squared, but neither way the quantity you typically solve for is the steady velocity that comes out of it. And so these two ways of solving it are merely a consequence of the form of this graph. In the laminar regime, the drag coefficient is a function of the Reynolds number. This is not the drag coefficient, but this is a constant, 64 over Re for pipe flow, and a different number for flow around a bowl or a cylinder, sphere or cylinder. And in turbulent flow, it's just a constant magnitude as a function of Reynolds number. So that's the essence, if you like, of external flows. I guess you might want to know that energy is equal to work, which is equal to force times displacement, which is equal to, in units, Newton meters. And power is the rate of doing work, equals Newton meters per second, or maybe think of it in terms of newtons times meters per second, which is the same as force times velocity. And of course, velocity is just displacement divided by time. So the two are linked in this particular way. Okay, and so that is our stuff from week 12 in terms of external flows, or topic 12 if you like. And finally, open channel flows. And so there are a variety of ways of looking at open channel flows. I guess what makes them different is that they're driven by gravity, essentially. And we can think, I think we call this width B. I guess we call this width depth Y. We've called lengths of these sections L. And the parameters that we've defined in terms of the Manning formula. Is that average flow velocity is equal to some coefficient, which is either 1.49 or 1, depending on the units we use. The Manning coefficient, which is like a friction factor, cross-sectional area of flow, the hydraulic radius, R sub h, to the power 2 over 3, the slope of the bed to the power half, and the volumetric flow rate. And so in addition to that, when we look at, so this is uniform flows. If we look at gradually varying flows, then we can also think of this as, instead of a volumetric flow rate Q, as you can think of it as a flow per unit width. So this is Q. So flow per unit width is just averaged or summed, if you like, over the total length of flow. And so for gradually varying flows, we can define the energy of the system as being equal to the depth plus flow per unit width squared divided by 2 times gravity times the depth squared. All in units of length, and so this energy is in units of length in this particular case as well, so I guess it's force per unit volume is really what it ends up being an evaluation of. And we can plot that on a specific energy versus depth diagram. Energy versus depth. With this line, which is y is equal to E as the boundary line, and one which defines flows relative to that, as this nose here being the boundary between supercritical and subcritical. And where this point here is equal to a Froude number of 1, which is equal to velocity of flow divided by the square root of gravity multiplied by the particular depth of flow, and this value is also given by the critical depth y sub c, and this is also Emax, Emin, not max, and the minimum energy is related to this depth of flow as 3/2 times this critical depth. So this point is related to the Froude number and the minimum energy through that. So those are certainly equations. If you know those equations, you don't need any others on the test. So not a massively short list, but at least one that is maybe serviceable. So if you have those at your and know how to use them, then you should have no problem working on the material of the test. Okay. All right. So let's do this. So as we've done before, let's go through the material. I won't stop with the equations because we talked about those, and explain in quick summary detail some of the formats. We've used the Moody charts many times. We've talked about it already. We've talked about the fact that this transition in flows occurs somewhere around this region here at a magnitude of about, I guess that's not quite right, 2000, which I guess is here. Laminar to one side, transitional, and then turbulent. And we're able to use the magnitudes of the Reynolds number, if we know what it is, to go up to the appropriate location and come across and find a friction factor which represents that flow regime. The important things to note are that within this laminar regime, the friction factor is a function of Reynolds number, an inverse function of Reynolds number. And in the turbulent regime, the friction factor is essentially constant. Much easier to solve when it's like that because you don't have to iterate on your solution. The Reynolds number is always given in terms of a characteristic diameter, and for us that characteristic diameter is the hydraulic diameter, and which we can calculate from 4 times the area divided by the perimeter, should we have such a geometry to deal with. Okay, so I think we've dealt with that before. We've talked about the energy equation, upstream, always, downstream, always. The pump head is on the upstream side of the equation and is positive if a pump and negative if a turbine. It's also related to the pump head is equal to the power of the pump in watts divided by gravity times density times volumetric flow rate. Sometimes we've written it as, the power being equal to gravity times the mass flow rate, depending on how you like to think about things. So that allows us to be able to put a pump within the system between locations upstream and downstream. And the head losses in the system come from either the major losses, which are incrementally small but sum to a large number, a friction factor from the Moody chart, either laminar, where it varies with Reynolds number, or turbulent, where it doesn't vary with Reynolds number and is constant, and length of the pipe, diameter of the pipe, velocity in the pipe. Not the velocities that are upstream or downstream, but the velocity actually in the pipe or the fitting. This we've always assumed is 1 for all our cases. I don't think we'll deviate from that. And if you look at the fittings are again given in terms of a coefficient. It's assumed that the flow is always turbulent and therefore it's constant, so just a number between 0 and 1 typically. And the velocity head, again, within that fitting, taking account for the behavior in the fitting. For networks, which would be good to look at, we talked about the different kinds of behaviors you have. In series flow, always, if you take a section across here, the volumetric flow rate Q, mass flow rate really, but density doesn't change very much. The flow rates should always be equivalent to each other as you go through those sections, which means that if you look at the heads as you go across this, they would change with each section. So the head loss in this case would likely be, if you drew the head loss along the length of this, which is going to be difficult to do, the biggest head loss is probably going to be here because it's the smallest pipe. So I'm not going to be able to draw this well, but the biggest head loss would be here, a smaller one would be here, a smaller one would be here, and a smaller one would be here. And so you can rationalize that based on the sizes of the pipes and what you expect the friction loss to be on a less efficient pipe in terms of allowing flow. For parallel flow, then the sums of flows into this tank plus this tank is the total flow into this tank. And the head losses, because they start off at the same head, total head in terms of pressure, elevation, and velocity heads here, and different pressure head, elevation head, and velocity head here, the head losses between these 2 points, upstream and downstream, have to be the same. So the head losses are the same, and the flow rates are some. So in some respects, they are the antithesis of each other. They're the opposite of each other. If you're dealing with loop systems, then it gets a little bit more complicated unless there's a simplifying factor. And that is that you can imagine two circuits that go through here. One circuit that goes through this upper path from points 1 to 2, and another circuit which goes through this lower path from points A to B, I guess, not 1 to 2. And so if you write the first route, which is this one, through the two pipes, this is the velocity in pipe A, this is the velocity in pipe B, here and here. And there are two head losses associated with this one, the one in the first pipe and the one in the second pipe. If you do the same Bernoulli or energy equation expression for the second route, you end up again with the same velocity in pipe 1, these are the same, but a different velocity in pipe this should be C, right? Not B. Oh no, sorry, that's wrong. These are the locations on the in the tank, large tank. So these are B's, and this is B. Sorry. Why don't I just take care of that by doing this? Yeah. So this is the pressure, which is 0 here, the velocity, which is 0 here if it's a big tank, and the elevation, which is Z. And the head losses are the first one in the first pipe, which is this, which would be identical between these two, obviously. And the second one, which is the head loss in the second part. Since the heads at this location have to be the same, the head losses in these two pipes also have to be equivalent to each other. And so that's one simplifying assumption that comes out of this. And so that's one constraint that we have here, is the head losses of the second pipes are the same. And so what we can do is we can write these two energy equations, and hopefully we can solve for either the velocity A or the velocity B except there's going to be a velocity term that comes up into these head loss terms, which is here. So there's actually 3 velocities within this, because there's velocities within each of these pipes. These velocities are going to go to 0 because they're in the tank. These pressures are going to go to 0 because they're on the free surface of the tank. And the elevations are just going to be the elevation difference. And so what we're left with then is a head loss in pipe 1, which will be a function of V1 squared, a head loss in pipe 2, which will be a function of V2 squared, and a head loss in V3, which will be a function of V3 squared. And so we have 2 equations but 3 unknowns. And so what we need to do to be able to solve that is to be able to note that the flow equation is that the inflow in the first pipe has to be equal to the sum of the flows in the second pipe. And so if we write these in terms of the velocities and the areas of the pipe, then we have another equation that links velocities 1, 2, and 3 in terms of known values of the cross-sectional areas. And so we have unknowns of 3 velocities here. We have unknowns of 3 velocities in these 2 equations, and so we can solve it. And there's usually some simplifying assumptions, and if you look at, I think maybe last year there was a 3-tank question that was solved, and so you can see the solution for that. This is a solution. We could go through it to be able to look at the flow through this. The basic question is, if you have flow through this system and you want to increase the flow rate by a factor of 30%, 1.3, what do you have to do in terms of adding, what's the diameter of the pipe you have to add? And so the first thing is to solve for the flow through the system where it's just going through the one pipe. And so with a single pipe, you can write the equation directly as we had it before. The upstream behavior, the downstream behavior for the tank, the pressures on the tank surface are 0, the velocities in the tank are 0, and the elevations are the only remaining parameter. And we write the losses in terms of the head loss in the first pipe, which is this, and the head loss in the second pipe, which is this, which are now 1 equation and 2 unknowns. So what we can do is that if we know what the relative diameters of the pipes are, then we can actually work out what the relative velocities are. Since we know that Q1 has to equal Q2, if the cross-sectional areas of the pipes are the same, then it means that V1 equals V2, and it means that these velocities here are the same as each other. And so we can solve that expression to be able to figure out exactly what the velocity is that goes through this system. If now we take this extra pipe, we know what the velocity is. If we want to know what the flow rate is, we just multiply by cross-sectional area, and that gives us a volumetric flow rate, and that's the flow in one pipe. We'd like to be able to make that flow equal to 1.188 times 1.3, which is this component here. And so we'd like to add a second pipe so that we end up getting that behavior. And so what we'd like to do is we'd like to know exactly what the flow rate is. So now we know the flow rate within this pipe will be Q is equal to whatever this amount is, which is 1.54 cubic feet per second. So we know that. And so we know that has to be the amount that comes through both this one, Q2, and also this one, Q3. And so what we can do is we can calculate, again for the system, the head loss going across the system is equal to the change in head between the upstream and downstream tanks, and the head losses between first pipe and the second pipe in sequence. So this pipe and this pipe. And since we know the flow rate in this, what we don't know is the flow rate in the second pipe, but we do know this, then we can use that to be able to write this equation in terms of, just in terms of V2. So it ends up being written in terms of one equation in terms of V2. And so we can solve for the magnitude of the velocity that comes out of this pipe. Once we know the amount that is coming out of V2, we know that the remaining amount has to come out of the second pipe, which is this, or third pipe, I guess, in this particular case. And so since we now know the amount that comes out of Q2, we know the amount that we need to get through the third pipe. Since we know that this is equal to this plus this, then we can calculate this as being equal to Q1 minus Q2. So we can merely rearrange this. So that is this. This is what we want to know, what the flow rate is. And we can write this flow rate within this pipe as being equal to just the difference in the two flow rates, the one coming out of the system out of pipe 2 and the one going into the system in pipe 1. So we can calculate exactly what that is. And so now we know that the total head loss through the system going through this second route from A to B, but going, let me do this, going from A to B, but along this route through here and up to this, of course. We can write an equation for this, and the equation for this is given by this expression on the bottom. That is, the head drop is equal to the head loss on the first pipe plus the head loss on the second pipe, this pipe plus this pipe. We can write those in terms of the friction factors. This is the velocity in pipe 1, this is the velocity in pipe 3, and so we know each of these velocities. We know that the velocity in pipe 1 we've calculated, the velocity in pipe 3 we've calculated. We know it has to equal this head drop, which we know. We know the friction factor, length and diameter of the first pipe. And we have to calculate, we know a length of the second pipe, we know a friction factor for the second pipe, but we need to calculate what the diameter would be. That's the only unknown. And so if we substitute everything into this that we have, the only term left to solve for is the diameter. So it's a little convoluted, but let's just make a walk through it again just to explain what's going on. We want to calculate what the diameter of the extra pipe is so that we get 1.3 times the flow if there's just one pipe. So we first have to calculate the flow in the one pipe system by writing Bernoulli between the upstream and downstream. We know the friction factors, and so we can calculate what the flow is through the system. Once we know that flow through the system, we can multiply it by 1.3, that gives us the total flow. Once we know what that flow is, we can calculate the flow through the top circuit, because now we know that we can write Bernoulli again between A and B. We know that the flow rate, the velocity through the first part, is now 1.3 times what it was before, and so the only thing we want to calculate is the new velocity V2. So once we've calculated the velocity V2, then we know what the flow rate is through here, which is Q2. And if we know the flow rate in this arm, the flow rate in this arm, and we want the total flow rate here to be 1.3 times the original flow rate, then the flow rate Q3 has to be equal to the inflow Q1 minus the one we just calculated for Q2. So we just calculated this. So the only thing that we don't know is the flow rate, the volumetric flow rate in the lower pipe, which we now have. And once we have this volumetric flow rate in the lower pipe, what we can do is we can take the circuit that goes through here, then down through this lower pipe, and we can write Bernoulli in terms of that. We know what the velocity is here. We know the flow rate through here, so we know the velocity V3 also. And we know the head drop between them is ZA. And so the only thing we don't know is the diameter of this pipe. We know the length, we know the friction factor because we've been told that it's constant, and we don't know what the diameter is. And so the only thing that remains to be solved for is the diameter right here. So a bit convoluted, but that's basically the way to be able to do it. Okay. All right. External flows. We talked about ways of being able to calculate either lift or drag. By convention, we've said already that this is basically an Euler number with a half in it. So you could rewrite this as an Euler number where this is length over area divided by a half rho v squared. This term doesn't belong in an Euler number, but this is basically a pressure of lift or a pressure of drag. And we can define the lift coefficients or the drag coefficients in terms of this. If we know what these magnitudes are from tabulations, and we know what the velocities of flow are, then typically we can calculate what the lift or drag forces which are applied on our structure. So it's the same, actually this is the same problem in solving for flow in a pipe, where you have a friction factor, but here we have a coefficient of drag, and we have this transition between laminar and turbulent. And the difference between these are that in pipe flows, we're not interested in the force on the pipe so much, but we're interested in the drag that the flow has exerted on it and slows it down, and therefore we can calculate what the pressure is that we have to drive it. So we can calculate the pressure loss in the pipe as a function of this friction factor to get a given flow rate. For external flows, the flow is slightly affected by the object that's put in its path, but what we'd like to know is, given a flow rate around this, defined by the particular Reynolds number, what's the coefficient of drag or lift? And if we know what the coefficient of drag or lift is, then we can calculate this if we know other things about the flow regime, the geometry of our object, and the fluid that's flowing past it. So that's typically the way of dealing with it. There are two basic solutions, one for laminar behavior. And that is, it's a force balance between, say, a buoyant force, a velocity going upwards, which is a drag force. A velocity as this sinks going downwards. A weight, which is applied here. And the drag, which would be applied going upwards. So if you do a force balance, you end up with the weight, drag, and the buoyant force. You can calculate what the weight is if you know the volume and the unit weight of the material. You can calculate the buoyant force if you know the displaced fluid and its mass, unit weight rather. And you can also calculate the drag coefficient by merely rearranging this term here in terms of drag, substituting it into here, realizing that once you've substituted in for d being equal to, what would it be? Coefficient of drag times a half rho, I'll say v squared times area. So you can substitute this in for here. You know what the velocity is, you know what the density is, you know what the cross-sectional area is, but you don't know what the coefficient of drag is. But you do know that if it's a laminar flow, then this is equal to, say, some constant divided by Reynolds number, which is the same as some constant divided by a Reynolds number is a velocity, a density, and a length, maybe lowercase d for diameter, and a viscosity. And so here in this equation now, we'll have one unknown value of velocity that we can solve for, where we know everything else. And then all we have to do then is check that the Reynolds number is appropriate for laminar flow, and then that's the problem solved. And so that's basically the solution that you see here. So two types of solutions. One for laminar behavior, which is what we've done here. So you do force balance. You write this force term in terms of a drag coefficient. You resubstitute this into here, and then you substitute the coefficient of drag into this to be able to solve for a single value of velocity that comes out of the Reynolds number. If the flow is turbulent, such as this second example, you go through exactly the same procedure. You write a force balance. Again, you substitute into this expression the coefficient of drag, which would be that drag force is equal to coefficient of drag multiplied by a half rho v squared times an area. So if you substitute for this, you have a term that includes v squared, and rather than now substituting for a coefficient of drag which is a function of Reynolds number, now coefficient of drag is constant. It's not equal to a constant divided by a Reynolds number. So this is for turbulent, and this is for laminar. And so they're just solved in slightly different ways. It's actually easier to solve for turbulent flow because you don't have to do the Reynolds number evaluation, Reynolds number substitution. And so you can check through that to figure out how to do that. External flows, same kind of idea. You can calculate what the drag is on an object if you know what the velocity past it is, because you can calculate that the drag force is equal to density velocity squared across sectional area. This is an area, and this is the coefficient of drag. And so if you want to get the forces that are applied on an object where there's one specific shape but also a second composite component, then you just sum up all the values of the drag forces that you use to be able to do it. And then that's the force that's applied. In this particular case, you could actually calculate the point of action on these, and you could calculate what the moments are that are applied. And finally, open channel flows. Open channel flows, we talked about definitions of mainly uniform flows, which are the simplest, gradually varying flows where we use energy diagrams, and rapidly varying flows, which would be hydraulic jumps, which we spent much less time on. We made the point that open channel flows are merely driven by gravity, and there's a difference between uniform flows and non-uniform flows. Uniform flows being that the depth of flow is the same upstream as it is downstream. And so by definition, if you look at it, the velocity squared over 2g term has to be the same upstream and downstream because it's the same cross-sectional area, so the same velocities. And so the energy grade line has to be parallel to the hydraulic grade line, which has to be parallel to the slope of the bed. So as a consequence of these, this value of change in depth as you go downstream has to equal 0. And so we can calculate some very simple expressions for uniform flows. For non-uniform flows, the only one we'll deal with are gradually varying flows. We don't really need to do this derivation, but we noted that if we want to calculate flows, and I did it wrong on the first page, I guess, is that this is equal to volumetric flow rate, and this is equal to average velocity. So this is a function of this coefficient, which depends on, for us it should always be 1 because we're using SI units, the Manning coefficient, hydraulic radius, and the inclination of the bed. As a number of 1 over x. I should make this change, right, early on. So remember I made that mistake, so don't forget that. So that's this. Hydraulic radius and slope of the bed. If you use composite sections, then you can typically divide the channel up into portions and being able to solve for those individual portions. Probably this isn't the best way to do it as an average value. Probably the best way to do it is as a compound flow, where you look at summing up the flow in this portion going into the page, which is this amount, the flow in this portion, which is this amount, and the flow in this portion, which is this amount. We have to be careful in when we calculate the hydraulic radius, which is the area divided by the perimeter. Then the area is clearly, for this one, is this. But the perimeter is only the wetted perimeter. It's only this combined length here. It's not, it ignores this part here because this is water that's flowing downstream, and the part on the left and the part on the right are going at the same velocity to each other, and so it's not rubbing against the friction of the channel. And so that needs to be, I need to be careful about that. And the third part is this flow rate in the third channel. We can look at minimum and maximum, so flow cross sections to be the most efficient. Did an example with this to calculate that. I'm not going to spend much time. We did talk about gradually varying flows, where as you flow downstream, I'll just flip back to this. As you flow downstream, no longer is the slope of the upstream portion the same as the downstream. The depth is therefore by definition not the same as you go downstream, and so the velocities in this particular case, the upstream velocity has to be much less than the downstream velocity because it's a smaller cross-sectional area just by continuity. And so the bed, the free surface of the water, and the slope of the energy grade line are no longer coincident. And so that's by definition a gradually varying flow. And so we define these in terms of behavior. And if we have a particular energy within a flow, we can define the energy of that flow, which is this. Y is we've drawn this diagram before, but it's worthwhile drawing again. Q is the flow, Y is the depth. I think we often use B for the width of the channel, and this is just a 1 meter flow width. So this is a flow per unit width, and so that's what Q is. And so Q is flow per unit width, Y is the depth of the flow, this is gravitational acceleration, and this is the energy. So if you know what the energy of the flow is between an upstream point and a downstream point, then you can use this to, if you conserve, if there are no losses within the system and it's horizontal, say, then this would be a straight line. And you could calculate what the energy was at the upstream. And if you put a constriction in this and still have the same flow velocity, you would be able to get a subcritical flow, which is everything above this line here. This is the Froude number is equal to 1. Froude number defines the magnitude of the criticality, I guess, in the system. And the upstream behavior in terms of a subcritical flow, which is deep, or a supercritical flow, which is shallow. And so I guess you need to know these expressions, or you might need to know these two expressions to be able to define that. This is the explanation of what's going on. It's really related to the fact that at supercritical flow, the flow actually occurs downstream, which is faster than the wave speed upstream. So the downstream flow can't communicate, send information back to the upstream. At subcritical flows, it's flowing slower. The downstream flow is slower than the upstream acoustic celerity wave velocity, so it can send information. And so in terms of these, I guess this is the other relationship, is that this nose on the energy line plot is the minimum energy within the system and is given by a particular depth, which is the critical depth. Critical depth at which the minimum energy occurs, which is also the place where the Froude number is equal to 1. And these two terms are related by the minimum energy is equal to 3 over 2 times yc. And I should check that we wrote 3 over 2 rather than 2 over 3. Yeah, we did. To be able to do that. And so we went through an example to be able to illustrate this of a horizontal bed with an upstream flow with a sluice put in it to be able to explain what's going on. And if the slope of the bed is horizontal and there's no energy loss within our system, then both of these terms go to 0. So this is inviscid means no energy loss, and S0 means horizontal bed. Then the upstream and downstream magnitudes of the energy have to be the same. And if they're the same, then they mean they must lie on the same energy line, E1 equals E2. And so if you have an upstream flow which is subcritical, which would intersect this curve for a particular flow rate, which might be this red one here, then this would be, if you know this height, then you can calculate from the curve exactly what the magnitude of the energy is, because it's this value here, down to here. And you know that when you constrict it, so long as the flow doesn't change, as long as Q1 is the same as Q2, then you'd come along this line. And as you go downstream, the only condition that this can take is going to be on this line at this point. If you wanted to look at a flow for this same flow rate, which was on the verge of criticality, was just the critical flow, then it would be this point here, the depth would be this, and the energy would be this amount. And so you can use that to navigate your way around and to determine exactly what flows are. So in other words, if you start off with here and you put a constriction within this to be able to make the downstream flow switch from this mode of subcritical to a supercritical flow, then because they have the same energy, because there's no energy loss in the system, if they have the same flow rate, then they're on the same specific energy curve for E is equal to y plus q squared over 2gy squared. And so if you know what the single flow rate is, and you could calculate as a function of a whole variety of different depths from y equals this to this to this to this to this as you go down through here. And if you substitute the value of y from this value all the way to 0, you'd end up creating a curve of energy as a function of y, which would look like this. Well, this one here. And it would also have a root that comes through here below this, but we don't care about that. And so the two locations, if it has the same energy, it can either be at this point or it can be at this point. And if you know it's at this point, then you know that the downstream depth, once you make it supercritical, has to be not the location of this, but it has to be equal to this particular point here. And you can calculate what this depth is. So maybe to summarize, I'm not sure we need to go through the remainder of this, which is probably good for you, is that if we have a flow, well, let me do this, clean this up. If you have a flow between an upstream location where you know the flow rate Q1 and the depth, you know it's on a horizontal base, so by definition the energy, the loss on the horizontal base of the driving flow is zero. If it's inviscid, then the energy loss of the system is also zero. And so merely the energies upstream and downstream have to be the same. So if you were to draw a energy versus depth curve by putting the depth equal to a series of depths upstream, starting off with this one, which is whatever it is, and then going progressively shorter, and calculating the value of this expression as a function of changing the values of y for a given flow rate, you'd end up with a curve that looks like one of these. Or I should do it on here. A curve that looks like one of these. You know when the water level is up to this is the depth, and therefore the energy has to be this magnitude down the bottom. You know that then if you put a constriction in here to get it beyond this point, which is the critical point, then you'd switch from being subcritical to being supercritical. And if that's the case, then the depth that you'd exist at would be at the same energy level, but where it crosses this lower part of the curve. And so the downstream depth would be this depth here. And so you can calculate the upstream depth and the downstream depth on the same energy line merely by the fact that we've required that they have the same energy because it's inviscid and it's a horizontal base. And I'm going to leave it at that. There are some other materials to go through, but why don't I cut you a break and not go through those? So that's about it. So just to summarize, we talked about what the individual components should be. 3 equations, one on pipe networks, which we talked about both parallel and tapering, and also branch networks and how to solve for those. External flows, we talked about how to use the coefficient of drag equation, which is equal to something like this, to be able to solve a force balance for a drag or a lift and solve for the magnitude of velocity, typically, either for laminar or turbulent flows. And we also talked about using open channel flows and this idea of specific energy, which is that specific energy is equal to depth plus flow per unit length width squared over 2g y squared. I think that's right at the bottom. Yes. And as I say, I think there's nothing on this test that isn't covered in both the concepts and the expressions that are on these first two pages, which we've just gone through. Okay, so I'll leave it at that. Good luck. Great having you in class, and I wish you well in on the test and in your careers. Take care. Bye.